Okay, so people have to see a solution of the homework problems that we did in class today. So here it goes. So this is 1715D, all right, and this was the specific case where you're neutralizing an acetic acid solution with sodium hydroxide using 50 milliliters of a 0.15 molar with another 50 milliliters of 0.15 molar. And the thing about this that is special is that since you have the exact same amounts of the exact same concentrations, you know that you would have the same number of moles of this compound right here as you would of this compound right here. All right. So, and you can calculate the number of moles using this formula right here. Molarity equals moles divided by volume. Make sure that your volume is in liters, because again, your units for molarity are moles per liter. That's why the volume has to be in liters. So you get this number of moles of the acid, this number of moles of the base. And what makes this special is that's exactly 1 mole of this per 1 mole of this, which means the solution that you would have at the end would be at the equivalence point. All right. So remember, when you have this, this is considered a salt. It's an ionic compound. So since it's dissolved in water, you'd actually have just free Na plus and acetate swimming around. All right. By the way, there's some questions about how to write the formula of acetic acid. I went ahead and wrote it the way that they did in the book. What I want to point out, though, is a lot of times it's written like this with the H at the end. And the reason for that is that this is the structure right here. So if you look, where is that? So this is the hydrogen which would get donated if it's acting as an acid. And the reason, notice that it's bonded to the oxygen. That's why they typically draw the formula like this. The reason that the book puts it in the beginning is, remember the rules for formulas of acids. Typically the hydrogen goes first. Honestly, I've seen acetic acid more commonly drawn like this. All right, but either one should work. So anyways, you have free, since it's an ionic compound, you have free acetate swimming around. All right. So we could calculate how much you would have. So since you've got 0.0075 moles of the compound overall, you'd have the same number of moles of acetate because there's one acetate ion per one of these units right here. All right, and this would be in a total of 100 milliliters. All right, and again, that's going to come from adding up the total amount of volume. Remember, you've got 50 milliliters of your acid solution, 50 milliliters of your base solution. That makes a total of 100 milliliters of solution. All right, so we could do a little bit of math here. You should get 0.075 molar of the acetate ion. All right, so what we're going to do, and this would be the same if you were to if someone were to just ask, what would be the pH if you had 0.0750 moles of sodium acetate and you dissolved it in 100 milliliters of water? All right, they would be the exact same thing. All right, so we can set up a little chart like this. All right, we're going to lose a mole of this. We're going to gain moles of these two things right here. And with this reaction, since we're considering this a weak base, the thing that would be relevant is the Kb. All right, so the Kb for this base reaction could be expressed this way. So now we just need to know what the Kb is. All right, so the way that we're going to get that is through knowing what the Ka of acetic acid is. And this is actually located in the index of the book that you're using. But what I also wanted to point out is that the data is also found in the data booklet, which most of you guys now have. All right, you will notice that the values are a little bit different between those. All right, and just remember, depending on the source that you get your data from, they can be a little different. So don't worry about if there's a difference between what your book says the Ka value is versus what your data booklet says. They're still pretty close. All right, so starting with the knowledge that the Ka of acetic acid is this right here, again, that's acetic acid right there, we know that the Kb of its conjugate base would be this right here. And you can get that just by doing the 10 to the minus 14th minus the Ka. And so we know that this, the Kb, because it's the same as that thing right there, we could use right here. We could plug it into this equation right here. Eventually figure out that X is this. And this is your hydroxide concentration. That would then give you a POH. And from that, you could calculate the pH. All right. So one thing I do want to point out, if you were to, is that in that same problem, 1715, you should also be able to do A and B. All right. I'll leave that up to you guys to figure out. If you have a question about that, you can ask in class on Friday. One hint that that I'll give you is to do B. Draw a pH curve. All right, draw a pH curve and notice how much of the materials they're saying to add. There should be something that pops out in that particular problem. Okay, so in the next problem, which was 1717, you're going to have this reaction right here. All right, this compound right here is called aniline. And the one thing about this this problem is that even if you don't know how this would act as a base, in the problem it is specifically mentioned as being a base. All right. So what we could assume about it is if it acts as a base, it's going to accept an H plus, all right, from an acid. All right. So if this thing accepts an H plus, all right, it's actually going to end up making this. This would be considered an ammonium salt. All right. So you might remember. Let's pretend that instead of having this part right here, it was just another hydrogen. Then this would be NH3. All right. And when NH3 gained reacted with an acid, it made NH4Br. All right, this is just the same thing where all we're doing is we're adding one more hydrogen, and then this would have a +1 charge. All right, so it would actually be this. When this thing accepts a H plus, it becomes this right here. All right, so what's left from your base, from your acid would be Br minus. All right, but we could write it like this, where it's the salt. So what you really have is this cation swimming around in the solution, this anion swimming around in the solution, and if you let all of that water evaporate, you'd be left with a solid material, which would be this material right here. All right. So, okay. So essentially, the problem becomes: what would the pH of this salt be if you dissolved it, if you dissolved that much of the salt in a certain volume of water? All right. So the way I went ahead and did this is just to say, all right, since we've got the same concentration of both, we could pick any volume. All right. If we had 1 milliliter of this, it would require 1 milliliter of this to neutralize it. I just decided to say, let's say that we have 1 liter of the acid solution and 1 liter of the base solution. And that makes the math a little easier because I could just say, all right, we have 0.200 moles of this, 0.200 moles of this, and that would give 0.200 moles of this material right here. All right, so that would be the number of moles of the, so again, this is the conjugate acid of this weak base right here. All right, so that's how many moles you would have. You would have it in 2 liters because you're doing 1 liter of each of these, so your final volume would be 2 liters. That means that in the end you're going to have 0.100 molar solution of this conjugate acid. All right, so we take that conjugate acid, which would be a weak acid, and we react it with water, and it's going to do what acids do. It's going to donate a hydrogen, and if it does that, we could write this reaction right here. So some useful information that we need. All right, we need to know, since it's we're doing an acid reaction, we need to know a Ka. All right, if you look in the appendix of the textbook that you're using, you'll find that it gives a Kb of this material right here. All right, which is the same as the aniline. All right. Well, again, aniline is nothing but the conjugate base of this right here. All right. Another way of saying it is that this right here is the conjugate acid of aniline. All right. So since this is the Kb of aniline, and that comes from the appendix, we could calculate the Ka of its conjugate acid, and that gives this right here. All right. Hopefully you're getting used to that. All right. If you know the Ka of the acid, you can figure out the Kb of the base the conjugate base, and vice versa. All right. So we could set up a little chart based on what we know. We could set up our Ka expression. All right. Again, it's going to be these two things right here on the top, this right here on the bottom. All right. And we're going to use the Ka, which we recently determined. We're going to set it up. We will do our calculations just like we normally do. All right. Since it's a weak acid, we can assume that 0.100 minus x is roughly the same thing as 0.100, and we end up getting a pH of 2.82. All right. So one thing about these problems that I do want to point out as far as the IB expectations is the only types of places that they would expect you to know the pH would be either when you haven't added any, if you're doing a pH curve at the point where you haven't added any yet, so it would be pure weak acid. When you're at the equivalence point, which is the type of question that we did right here, when you've added exactly 1 mole of an acid versus 1 mole of the base, or when you've added half of the amount, and that's going to be that type of buffer problem. All right. And again, that's hint. That's going to be the one that you would see in part B right here.